Hello, and welcome to the U.S. Center. We are about to begin our last NASA Hyperwall talk here. It is with Laura Rogers, and she's going to be speaking about 50 years of Earth observation with Landsat. Please take your seat. Thank you. Let's give her a round of applause, please.
All right. Good afternoon and welcome to the U.S. Center on the last day. We're super excited to have you, and then I think we're all pretty excited to go to sleep. So hopefully you guys are looking forward to that too as well. So the last thing we're going to talk about today is our last Hyperwall talk, but we're going to talk about the last 50 years of Landsat. And so we're going to start with where we started, where we're at today, but then where we're going into the future. So just a little background on Landsat. It's a series of satellites. We're on Landsat 9 now. Thank you for that. This is part of a NASA USGS partnership. So we work together to make this happen. This is the longest continuous collection of Earth observations, and it's really focused on our resource management. So let me find my clicker. All right. As far as the sensors on board, we actually have currently have two sensors, but over time they've really evolved and improving in our spectral radiometric temporal resolutions of these images. Right now we have both a thermal imager and a land imager. This is doing an overview of a flyover of Earth. But the satellite travels at 7.5 kilometers per second, and it circles the globe every 99 minutes. So I find that really amazing. Landsat will image a swath of about 185 kilometers, and for my U.S. friends, that's about 115 miles. And it completes 14 orbits each day, and therefore comes back every 16 days. So I had to read that because I can never remember those statistics, but I will try to avoid that in the future. All right, so again, I mentioned we have a series of 9 satellites. We started back in 1972, so we're at 50 plus years. We had our 50th anniversary last year. We really celebrated at the PICOR conference, but we continue to celebrate. But Landsat 1 through 3 really consisted of one instrument called the multispectral scanner. As we moved into Landsat 4 and 5, we continued with the same bands. They had 4 bands to continue. As we moved into Landsat 4 and 5, we called that the thematic mapper, but we added a thermal and a shortwave infrared band. Landsat 7, unfortunately we lost Landsat 6 at launch. Landsat 7 added a panchromatic visual as well. As we move into Landsat 8 and 9, we actually have two instruments on there, operational land imager and the thermal infrared sensor. And I would be remiss if we didn't talk about Miss Virginia Norwood. And a lot of the conversations that we've heard today, or in the past week or 2 weeks, we've talked about code development a lot. So I found it really intriguing to share this anecdote that as Virginia Norwood found out that NASA was looking to do a satellite mission for resource management, she really started with a survey of what those potential applications could be. So she went out and talked with farmers. She went out and talked with water resource managers and found out what they wanted out of a satellite like this. And it really opened her eyes on the different types of instruments and the different types of observations that she could be using, which I find intriguing, especially today as we're talking, 50 years later, we're still talking about the importance of code-development and understanding how different things could be needed. I also love this image here to really prove out the capability of what is now the multispectral, I forgot, the MSS. She put it on the back of a truck and went out and took a picture to show that not only could it get those 4 bands, but it was really provided beautiful pictures. All right, now we're going to go into the fun stuff, really being able to look over time on how we can capture this. So this is the devastation and recovery of the Mount St. Helens following the 1980 eruption. And you can see over time, we really had a loss of vegetation, but being something that's gone over continuously at the same time each day, we can really see as the vegetation comes back and see the changes on Earth, which is really, again, the power of a Landsat instrument. A lot of these I'm just going to run through because they're just beautiful imagery. Another really key part to watch is how our water is changing. And again, looking at the resource management, that's something that we can really pick out in some of this imagery. This is another fun one, and this really kind of captures some of our climate change and what we're seeing as the temperatures begin to warm. So this is the Columbia Glacier leading into the Prince William Sound in southeast Alaska. And what we're looking at is the edge here of the terminus. What's also really interesting is you can see it slows down just right as it went through the two peaks here. As it continues to retreat really rapidly. This is moving faster than I can speak, but looking all the way back. So again, we can see where it is back in 1986. It was fairly stable for quite some time and then rapidly retreated. I'll let that play through one more time so you can see it. But again, you see a pause at the peaks as it came together and slowed, and then it continues to go. And this is just a still image, but again, it gives the power of what we can view using Landsat. This is in 2016. You can see where it's fairly stable. 1 year later, you can see the crack beginning to form, and it's only 2 months later that you can really see this example here. And again, just being able to visualize it, to see it from space, track it over time, really leads to some of the power. All right, a couple things to note here. This is the rapid urbanization of Las Vegas. And you can see as we start in some of our earlier satellites, it's building out rapidly, but you'll also be able to watch how much more crisp the visualization gets. The resolution is truly improving. But another key point here is, again, seeing this water and being able to track those the use of water as we urbanize at such large scale and pace. Here we go to Landsat 9. It's quite a difference as we go back. All right. This is just an image, and I'm going to go into the next one shortly. But this is showing the evolution of agriculture in Saudi Arabia. As you can see right now, the green, this is a false color image. The green is where we do have some vegetation. But you also see there's fairly limited water. This is in 2000, and within 12 years, you'll see a rapid change. So this is that same image I just showed you, just at a smaller scale. This is, 1987 through 2012. So 87, 91, 2000, and 2012. But again, this is agriculture in Saudi Arabia. So what does agriculture require? Water. And so they have to tap into the groundwater, which is sometimes greater than 1 kilometer in depth through the shale. Now, we don't know exactly how much groundwater is here, but we estimate that at the current pace of this growth, it will last less than 50 years. Now, there's not a lot of rainfall in this region either, so to refill and to recharge that aquifer, it's not happening at the pace that we're extracting water for these agriculture. So this is something, again, we can track this over time, we can see it, and we recognize that this is a significant water resource issue. Right. Now I want to get into kind of where we're going in the future. We're looking at can we advance and innovate what we're doing. This is just a still image of the Dixie Fire, the campfire in Sacramento. And it's just an image. But as we look at other ways to do this, this is the 2021 Dixie Fire. Now with this, we're showing the images. We're also bringing in different views from the VIIRS instrument on SUMI MPP. So what we're doing is we're tracking the spread of the Dixie Fire. So the yellow line is the extent over time. But bringing these two components together, we bring together the visual, but we also are able to track the fires and as the compounding impacts, right? So as we look at the fires, we can see the plumes and so forth. So all of this comes together. Over here is the cumulative area burns. And again, I mentioned innovation. So right now we have Landsat 8, but we also, hopefully this isn't too slow, but we also have Sentinel-2, right? That's not a U.S. satellite, but we work with our European partners very closely. So what this is demonstrating is that we can bring these together. So we're working on what's called a harmonized Landsat Sentinel product. It's called HLS. And what you'll see is that these two satellites have very similar spectral and spatial similarities. So when we can put this data together to really amplify what we can get out of it. When these data are used together and they're brought together and harmonized, we have a more timely and accurate product. So we can now provide coverage every 2 to 3 days at 30 meters. So this is how rapidly it can be collected when we bring them together. Additionally, we often have issues with clouds. We have breaks in data due to clouds. So again, harmonizing this data really brings some power to the data. This is just an example of an HLS product. This one is looking at NDVI, and now we have a 2 to 3 day refresh as opposed to what we'd have with only a Landsat NDVI product. So you can see the greenness increasing through the summer months, and as we get through summer and we go into fall, you'll see it. The crops are becoming, going into winter, less healthy. All right, so what we're looking at here is our last piece. We're looking at Landsat Next. What's really interesting here, that it goes really fast, is right now we have the 16-day revisit. As we go into Landsat Next, they're looking at a constellation of satellites, what would give us a revisit time of every 6 days. Not only are we increasing the revisit time, but we're also increasing the resolution of these instruments. So we're continuing to innovate, we're continuing to discover and push the limits into the next phase. And with that, I will close with the 50 years of Landsat. Are there any questions?
Just raise your hand and I'll bring you the microphone.
Hello, my name is Nikita, thank you. Do you also monitor the air pollution level through your Landsat? And if yes, how precise is that compared to the on-land monitoring system?
So we do have a lot of instruments and satellites that can look at different aspects of air quality. So whether it's PM 2.5 or carbon or what have you. We don't particularly use Landsat for that. We have different instruments that can monitor that. So we just recently launched a mission called Tempo, and that is over North America, but it is looking at different qualitative factors of air quality.
Yeah, because that's what I saw before the event on the screen. That's why I thought I'd ask about that. Okay. And how precise is that compared to on-land monitoring? Have you compared that?
Of course, you're going to have very different resolutions. I don't know the specific resolution of the Tempo instrument, but again, we do a lot to bring together our satellite, our airborne, and our in-situ observations. So we bring those together to give us the best picture of air quality. Now, as far as Tempo, and again, this is only over North America, it has a temporal resolution of every hour. So every hour, you're getting a new picture of what your air quality, atmospheric composition is looking at. So you can see the spatial movement, but I don't know the exact spatial resolution off the top of my head.
And the second question, you mentioned going from 16 days to 6 days. Do you think you can reach like live within seconds or minutes, every minute monitoring? Is that
well, possible? Every 6 days is the revisit time.
Right. Do you think you can ever reach something within hours or something, or minutes?
Technology continues to improve. We're going to continue pushing the boundaries, but I don't know that we'll get to that point. But, as technology changes, there could be new options out there.
I assume you capture some confidential information as well as public information. How is information shared?
all of our information is publicly available. So everything that we capture is shared through Earth Explorer, actually. So again, we're a partnership with USGS, so they do some of the operational components of that, but everything is shared online, freely available to the globe, to the world.
This is the last NASA Hyperwall talk here at COP28, so get your questions in now.
Thank you. I'm Sean Mooney. I'm the Dean of the O'Neill School of Public and Environmental Affairs at Indiana University, and I'm curious as to what can we do to best train people to use this type of information, and is there something that we could do better, in your opinion?
That is a fantastic question. I think that is the question of the decade, right? We have a collection, we have a whole wide range of information. This is just one of our missions, right? We have a collection of missions and collection of data. We provide what's called advanced remote training. No. It's just RSET training. It's called RSET training. But it's how to access the data, how to use the data, how to best integrate that data with other products. And we break it down into various different components. So if you're interested in coastal erosion, if you're interested in freshwater resources, we have very specific training on how to use it for those applications. Now, as far as how could we do it better, that is the question that we are continuously looking into. I can't speak. I'm sorry. So we want to reach. I think that one of the things we can do is reach the younger generations, right? As they're growing up, understanding that this is available and bring it into some of the education that we do. We have programs that do some of that, but the GLOBE program again has train the trainer type of thing. So you can train educators, you can train STEM professionals, but getting that out there more broadly and making people aware of all the information we have is probably one of our greatest challenges.
All right, if there's no more questions, another round of applause.